Hello, welcome to this webinar about building embedded Linux images with the Yocto project. My name is Brandon Shibley. I'm a field application engineer with Toradex, and I'm coming to you live from Seattle. Thank you all for coming. This is the first part of a two-part series about using the Yocto project. So this part will be more introductory, while the second part will be a little more advanced and will focus a bit more on strategies for customization. Jeff Oyser-Mixon of the Yocto project was slated to accompany me in this presentation and introduce the Yocto project, but unfortunately he had to cancel, so I apologize that you will have to listen to only me for the next hour. This is the outline for the webinar. To set some of your expectations, I see this as being a practitioner's guide to the Yocto project. It's basically tailored by the experience I have working with customers to address their needs in building custom Linux images for their products. So this webinar will be quite applied. About half of it will be a demonstration. That said, I recommend checking out the documentation hosted by the Yocto project. It is really quite good, certainly above average as far as documentation goes. I will introduce Toradex and the Yocto project. I will cover the major concepts of the Yocto project and introduce you to the typical tools and structures used by it. And I'll describe how Toradex utilizes the Yocto project and ultimately just demonstrate how you can use the Toradex Yocto build system. First, we'll start with a little about Toradex. Toradex was founded in Switzerland in 2003. We have offices throughout the world. As I said, I'm coming to you from our office in North America, located in Seattle. We have an office in South America, our headquarters in Europe, and several offices in Asia. And in this way, we support customers around the globe. Toradex is a provider of ARM-based system-on modules. They're used in many different industries, including medical, automotive, test and measurement, digital signage, point of sale, and so on and so on. We use system-on chips from NXP, formerly Freescale, as well as NVIDIA and Marvell. And we offer board support packages and free technical support for Linux and Windows Embedded Compact. And we've recently begun adding support for Windows 10 IoT, as well as FreeRTOS for our modules supporting heterogeneous multi-core processing. So I'm introducing Toradex for a few reasons. For one, they sign my paychecks, but I also see Toradex as a good case study for the Yocto project. Our main business is system-on modules, and we strive to make them more or less interchangeable. If you're not familiar with the system-on module approach, you can refer to the graphic here. The computer circuitry is consolidated to a small module, and you can use it in conjunction with carrier board in whatever form factor with whatever connectors you might want for a specialized embedded system. And as I was saying, Toradex makes pin-compatible modules to accommodate upgrading, downgrading, and otherwise evolving with new features and capabilities over time, without the need to completely redesign the rest of the system. And to that end, it's also important to make the software as consistent as possible across these products. And to do that, we leverage the Yocto project to create a common experience for system and application development among our products to facilitate interchangeability, not only at the hardware level, but also in software. We have a history of making contributions to the various meta layers and related projects of the Yocto project, and we've recently become an official Yocto project participant. Okay, so what is the Yocto project? I find that it's not the simplest thing to describe, but what I find awesome is that if you go to the Yocto project website, the first thing you encounter is this quote: "It's not an embedded Linux distribution, it creates a custom one for you." So this statement broadly indicates the purpose of the Yocto project while simultaneously dispelling its biggest myth, that it's a Linux distribution. And frankly, I'd like to leave it at that, but in reality, the Yocto project is quite a bit more than that. Officially, it's a Linux Foundation work group, which began in 2010. As an organization, it's an industry collaboration made up of a number of embedded computing companies. It establishes guidance and some standards regarding the tools and resources and practices used to build embedded Linux images. It actually includes a lot of sub-projects and incorporates other previously independent projects such as Open Embedded. And it includes support for various architectures, namely ARM, x86, MIPS, and PowerPC. In the Yocto project, a build system is a complete, almost fully contained development environment in which packages and recipes may be built. It's a Linux-based system, and as I said, almost fully contained because it does require some support of a Linux host system. There are a few popular Linux distributions that the Yocto project routinely verifies as officially supported to be used as a host distribution. The Yocto project build system includes tools, most notably BitBake, which we'll get to know later, but also other utilities, scripts, and such. It also includes a healthy dose of metadata. It includes recipes, configuration files, and such, and the amount of metadata in a typical build system is quite substantial, and is one of the ways that the framework enables such a significant degree of customization. Pretty much by definition, a Yocto project build system is built upon open embedded core, and we'll see more about that on the next slide. And I should point out that the Yocto project maintains a reference build system called Pocky. Again, we'll get to know more about that a little later. So let's talk a little more detail about the major tools and components utilized by the Yocto project. Open Embedded Core is a fundamental part of the Yocto project build system. It acts as the foundation layer for the build system. Open Embedded Core is the result of a refactoring of Open Embedded, now referred to as Open Embedded Classic, as a part of an alignment with the Yocto project. In fact, Toradex originally supported Open Embedded prior to our adoption of Open Embedded Core, which has ultimately led us to where we are today with the Yocto project. BitBake is the build engine used by Open Embedded. It parses all the metadata provided by the build system, which is used to schedule and execute tasks. Pocky, again, is the official reference build system for the Yocto project. Use of Pocky is not required for Yocto project compliance or compatibility, but it serves as a sort of working template and is often used as a basis for other build systems. Pocky was originally a fork of Open Embedded prior to the merger of all these different projects under the Yocto project. It includes Open Embedded Core, BitBake, and Metadata, which includes some reference BSPs and the Pocky distro. This can lead to a little bit of confusion given that the Pocky name can be associated with multiple things, both the build system and the distro. And there are a variety of other tools that are part of the Yocto project, some of which are listed here. OPackage is an embedded package manager. Hob and Toaster are UIs for BitBake, Toast specifically a web UI. Auto Builder is used for automated builds and testing. And the Eclipse plugin brings toolchain and SDK integration to the Eclipse IDE. Okay, let's talk about metadata. There are three primary types of metadata files, all of which are parsed by BitBake. Configuration files are used to set global variables used by BitBake. So some examples of those include BSP configurations, distro configurations, which define distro policy, user configurations, layer configurations, etc. So quite a few different types. Classes contain commonly used instructions, functions, and other stuff that is needed by multiple recipes. And they're defined in a BB class file, which can be then included into other files such as BB or BB append files. And finally, recipes contain instructions for building packages. They are very much like a cookie recipe. They tell you what components are needed and how to bake it. More specifically, they tell BitBake where to obtain source files, patches, etc. for packages, what runtime and build time dependencies exist for the recipe, and how to configure and build packages and more. Recipes are what BitBake builds. Both packages and images are defined by recipes, and recipes are defined in BB files and can be appended to using BB append files. All this metadata is organized into layers, and layers are important to the build system. These collections of metadata are called layers because they stack on top of one another. Metadata is one layer, and one layer may override or append to the metadata in another layer. OE core is the base layer of the build system, and BSP layers are special layers which provide support for specific machine configurations. And finally, application and distro layers provide application recipes and or distro policy. The Yocto project doesn't really distinguish between application and distro layers, so occasionally they're intertwined. And here we're actually having a look at the development environment as documented in the Yocto Project documentation. I don't want to belabor this diagram too much, but a few things we can note. See the metadata listed there in the dark green. So this is the kind of stuff we would find in layers. User configuration, the source mirrors with recipes, machine configurations in our BSP layer, and policy configuration as part of the distro. And that all gets fed into the build system, shown here in blue. And kind of the whole procedure that's shown with the arrows here is driven by BitBake. It's the engine behind all this. So it's pulling source, patching applications, configuring and compiling, and then ultimately generating packages. So the first part of this is probably not too surprising. That's our kind of standard build procedure: fetch, patch, configure, compile. And then the generation of packages is where things get a little more interesting as far as, build environment goes. We see here that actually the Yocto project is supporting RPM, dev, and IPK packages. And then it does some QA tests. These aren't exactly real in-depth QA tests, but they're at least some sanity checks, which are nice. And then here's kind of an interesting part of the whole thing: the package feeds. So to build an image, we wouldn't necessarily have to generate all these packages. You can build this stuff and just put it on a root file system. However, this whole system incorporates packages and the package feeds to generate the image and the SDK. And so the other cool thing about it is, let's say you already have a system with an image deployed, you can then point it back to package feeds and get packages built using the build system, and let the package manager deal with figuring out, dependencies and such. So it's kind of a cool workflow here, part of the Yocto project development environment. Let's briefly discuss alternatives to the Yocto project. My goal here isn't to sell you on the Yocto project, but one of the most common questions I get asked is, why the Yocto project and why not Ubuntu or something else? So I think it's at least worth doing a little comparing and contrasting. Major alternatives that I've listed here are mainstream Linux distributions, Android, Buildroot or other build systems, and non-Linux OSs. And based on what I hear from customers, mainstream Linux distributions, that would be like Ubuntu, Debian, Fedora, etc., are the most desired alternative, primarily because folks are used to working with them on their desktop. And in many cases, they've already built a proof of concept in one of these x86 distributions. Unfortunately, some believe that if the same distro ran on the embedded ARM platform, that their software would easily port. And that's not necessarily a guarantee. And for Android, which has steadily increased in popularity in embedded, it's fairly well supported on ARM platforms, but it still suffers from some of the disadvantages of a mainstream Linux distribution while also having some additional constraints. Although it's certainly a viable option, I find many customers interested in Android are ultimately interested in the look and feel of Android, which can also be obtained using other flavors of Linux, so they don't necessarily need to constrain themselves to Android. As for Buildroot, I won't make the case that you shouldn't use it. Buildroot's a good build system, although it is perhaps quite a bit less featureful. But where build systems such as the Yocto Project and Buildroot excel is in the freedom they enable to customize almost everything, so you can really tailor an image to your package, toolchain, security, and licensing needs. And this customizability is a really strong selling point in the diverse world of embedded systems. But in the end, I believe that vendor support is actually the most major deciding factor. Most people ultimately choose to use whatever is best supported by the vendor of their embedded computing solution. And as far as embedded ARM goes, the Yocto project is actually very popular. Many SoC providers are supporting it, perhaps more than other platforms. And in the end, I think all these options are ultimately viable for use in embedded. But the major considerations from my perspective are vendor support and configurability, which the Yocto project addresses quite well. Okay, so let's talk about the Toradex build system. It is based on the Yocto project. It features the Angstrom embedded Linux distribution, which is Yocto project compatible. This is in contrast to Pocky build system, which uses the Pocky distro. So that's one variation that you will see. We also have support for lightweight X11 desktop environment, and this is also another point of contrast with Pocky, which Pocky supports SATO, which is a different desktop environment. And the Toradex build system includes support for Toradex BSPs for our products and our own evaluation images. As far as versioning goes, our latest release is the v2.5 beta 3 release. It's based on Yocto release 1.8, which is the FIDO release, and it uses the Angstrom, the 2015-06 release. And then our next release will be v2.6, based on Yethro, the 2.0 release from Yocto, and the next Angstrom release. So that's what you can expect from Toradex. And then for sources, you can actually grab all the stuff that we're maintaining from our Git repo at git.toradex.com. And we also provide a handy repo manifest with basically all the meta layers used by the Toradex build system. All right, so let's just take a little closer look at the layers that make up the Toradex build system. There's, of course, Open Embedded Core and Meta Open Embedded, which includes actually quite a few other meta layers inside. So you'll find a lot of kind of common software packages there. And then these Meta FSLR layers come from NXP, formerly Freescale. And these have like BSP support for our NXP products. Meta Linaro, Meta Angstrom, Meta LXDE, and Meta Toradex. So Meta LXD and Meta Toradex are layers that are maintained by Toradex. So that provides a lightweight desktop environment. And then Meta Toradex provides a little bit of both BSP support and sort of application support. So that's a layer that may eventually be split into 2 layers. Similar split actually occurred with Meta Yocto as well, which formerly had both BSP and non-BSP stuff in the same layer. So we're looking to probably make the same split with Meta Toradex. Right, and the BSPs and images that are part of the Toradex build system. Looking at the BSPs available, I've listed those that we actively support. They're primarily provided in Meta Toradex or in Meta FSL ARM Extra, where we've upstreamed some of our NXP-based BSPs. In this list, the SOCs are listed on the left and the machine names used by the build system on the right. And for images, these are the ones that we sort of provide as part of our Meta Toradex layer. The default image that we ship on modules, so our modules actually come pre-flashed. At least they either come pre-flashed with Windows CE or Windows Embedded Compact and or our Linux image. So the Linux image that can get shipped on there or that we also provide for download on our website is the Angstrom-LXDE-image. So this is Angstrom-based with the lightweight desktop environment. The other recipe that we provide for an image is console-based, so without desktop environment, without X11. So a nice lightweight image. Still can be trimmed down quite a bit though. And then Angstrom, actually these bottom 2 have the Qt framework. So one of those uses X11 with the Qt, and the other one is Qt embedded without X11. Okay, and these are additional resources available. Certainly recommend the Yocto Project documentation, also the wiki on Open Embedded, and then from Toradex, you can check out our developer website, which is developer.toradex.com. And we also have a new community website, which I recommend checking out as well. There you can, it's very much like Stack Overflow. It's a Q&A style website, so really you can ask your kind of maybe unique questions which you're not finding answers to in sort of the standard documentation. So that's a great resource. And then also our webinars. So you'll find, for example, this webinar up eventually as a recording on our webinar site. And so the next thing I'm going to do here is transition to the interactive portion of the webinar. So we'll do a demonstration here. I will just need a second to switch over. Okay, so I believe you can now see my console. And this is the interactive portion of the webinar. I'm going to show you how to build an image with the Toradex build system. Again, it differs a bit from the Pocky reference build system, but as far as the Yocto project is concerned, they are conceptually very similar. and they share the same tools, basic structure, and such. And due to standardization, this walkthrough is generally applicable to any Yocto project build system. The differences you'll see, particularly in layers, machines, recipes, configurations, etc., are interchangeable by Yocto project design. Some of the basic instructions for what I'm about to show you are provided on our developer website. That's developer.toradex.com. I think we're also posting a link in the chat here, which has instructions about setting up this stuff from the Toradex documentation. Most importantly is what I'm not showing you, which is the prerequisites, and specifically installing the necessary dependencies for your host Linux distro. So you'll find that in that link. Additionally, we'll be using a tool called Repo, which you can also install using instructions provided on that page. Repo is a tool on top of Git that helps with managing multiple Git repos, and most of the other tools required are provided by the build system itself. So let's get started. So we'll begin by creating a Yocto directory, and then we'll use the Repo tool to initialize the build system inside of there. Now this repo init command creates local repositories for the meta layers used by the Toradex build system. By specifying the branch by name, we'll get the head of the branch, in this case Linux image v2.5. You can instead specify a particular revision. For example, I may want to synchronize with a specific Toradex image release, so I may specify a tag like this one here with refs/tags/tag name. And so now I'll be resyncing with the beta 3 release of our v2.5 image. We only need to execute repo init once, but it doesn't hurt for us to do it again here. And let's have a look at the remote repos here that we are syncing with. Ones we see: Open Embedded, Toradex, Yocto, Angstrom, Freescale, among others. So those correspond to many of the meta layers that I discussed earlier. Now we'll be using repo sync, which will actually synchronize the local repos with their corresponding remote repos. Since all of our local repos are still empty, as they've only just been initialized, it'll essentially perform a Git clone on each of them. Now this can take some time, a matter of minutes typically, so I'm going to go ahead and skip through it. Okay, let's have a look at what was created. There we go. We have a file called export and a directory called stuff, which has all the meta layers for our build system. To initialize the build environment, we'll source the export file. This sets up some environment variables and sets up a build directory if it hasn't already been created. The script only exports variables for the current shell, so you'll need to source this file anytime you start a new shell and want to work with the build tools. We're now in the build directory that was created, and we see within there that there is a conf directory with some configuration files. We'll need to make some changes to the local.conf file. And we're going to build an image for the Toradex Calibri IMX6 module. So I'm going to need to set the machine variable to Calibri-IMX6. We also need to add this line, which I'm going to paste into the file, which is a way of indicating that I've read and accepted the terms of the NXP/Freescale's in-users license agreement, which is necessary for some parts of the meta FSL ARM layer. There are quite a few other variables that can be set or changed in this file, so we'll revisit them later after we get to some building. And now we're going to, now we're actually ready to build packages and images for the Calibri IMX6. So as you've seen, once the dependencies are installed, it should only take about 5 minutes to set up and build environment and start building. When this build completes, we will have the same evaluation image we ship on our modules and make available for download at toradex.com. But before we go any further with building an image, let's look at the layers that make up our build system. Another configuration file that to have a look at is the bblayers.conf file. This file defines which meta layers are to be included into the build system. And we should recognize these layers from the stuff directory, which was created after executing repo sync. So again, having a look at those. And one final way to see the layers that are currently configured is to use the bitbake layers command. This shows us the layers that are configured, their location on the file system, and their priority to help us determine their precedence. So let's have a closer look at one of those layers. Meta Open Embedded is interesting because it contains a bunch more meta layers inside of it. And having a closer look at one of those layers inside of Meta Open Embedded, say Meta Web Server, we see how the recipes in the layer are organized. We see the recipes grouped by category, in this case HTTP, PHP, etc. And within those individual directories, or there are individual directories for each recipe. Let's have a look at a recipe file. For example, the recipe for Nginx, a nice lightweight web server. The first few entries are fairly self-explanatory: summary, description, homepage. License tells us the license that the package is distributed under. Depends tells us there are build time dependencies for this recipe. And source URI indicates the source files used to build the recipe here. The first is the source code, followed by a patch, and then some configuration files. A little further down here, we see some functions like doconfigure and doinstall. These functions are executed in conjunction with those tasks, the configure and install tasks. And again, we can use the bitbake layers utility to see more information about our build system configuration. Using it with the show recipes function here, we'll see all the recipes which are available to build. And in this case, I'm piping the command through less in order to easily browse the recipes. So here you really get a sense of just how many recipes are configured in the current build system. Okay, now that we've seen some of the layers and an example recipe, let's get to building something. We'll go ahead and build Nginx since we had a look at the recipe. We just type bitbake Nginx. Now this build process will take quite a while the first time, typically even for a single recipe. However, after a recipe is built, it will build much faster in subsequent builds. We see that there are 1,076 tasks that must run to build this recipe and its dependencies. 8 tasks are running in parallel since my build machine has a quad-core processor with hyperthreading, which reports that it has 8 CPUs. We can actually change this in the local.conf file if we want to change the number of concurrent tasks. As I said, this takes a while, so I'm going to go ahead and try and speed it up a little. Okay, let's have a look at what happened. There's now some new directories within our build directory. The one which we're most immediately interested in is out glibc. Inside of out glibc are a few directories. The packages created by our build are located in the deploy directory. I won't cover all these other directories, but a few of interest. The log directory is one place where you'll find bitbake logs. Sysroots is where you'll find root file systems for the both target and host machines with libraries, headers, and such to build against. And the work directories are where source is extracted, configured, and built. But let's take a closer look at deploy. Inside there's an IPK directory where all the built packages are, and a licenses directory which holds licenses for these packages. With IPK, you'll notice there are several architecture tune directories, and so we'll just have a closer look. And now we're seeing all the packages built under each of the architecture tunes, all of which are compatible with our target. We have these different architectures because some recipes alter the architecture features they build with. The reason we built so many packages to build the Nginx recipe is because all these packages were built by recipes that are somehow part of the dependency tree for Nginx. Ultimately, they don't all need to be installed along with Nginx, although many of them will need to be. And here we see the package for Nginx. To install this package on our target, we could take this IPK and any of its dependencies which are not already on the target and install them using a package management system. Using a package manager is really nice for this. Going a step further, we could even enable a feed server to serve these packages and avoid the need to manually transfer them to the target. But let's not get too caught up with this right now. We ultimately want to use these tools to build an entire custom Linux image. So let's turn our attention to image recipes. Now that we've built a recipe, let's look at building an image. These are the images that are available in our current build system configuration. You see a number of different images listed along with the meta layer they're provided by. And then let's look at the images specifically provided by the Toradex layer. Again, we saw these earlier. The standard evaluation image, again, that Toradex provides is the Angstrom LXDE image. And let's just take a look at that recipe. I'll just quickly skim over the recipe to keep it short, but one of the more interesting variables to note is image install, which is used to specify which packages will be included in the image. We also note that this recipe includes some other files. For example, this one here, TRDX extra inc. So let's have a look at that file as well. Now we see in this file that even more packages are appended to image install. Also note that some machines have some of their own additional packages specified using image install append. For example, some machines have applications or utilities specific to some of their unique hardware features. So you see most of the image recipe is simply defining the packages that will be included in the image. Okay, now what if we want to add more packages to the image? Well, the truly proper way to do it would be to create your own layer where we would maintain all our own customizations and create a BB append recipe for the image that we want to customize, and then append the packages to the image install variable. Alternatively here, I am going to simply add the same declaration to our local.conf file. So this is where user configuration is defined. And here we'll just put nginx added onto image install append. And here we can append one or more packages to the image install variable. And now any images built will now have these additional packages added. Okay, here we go. Time to actually build an image. Bitbake, Angstrom, LXDE image. What you'll see is that this looks very similar to the package build we did with Nginx, but now it's going to build a lot more stuff. And this process can take a long time. If it's the first image build we've done on the system, then it probably take a couple hours or more. So we'll try and make it go quickly. But also know that subsequent builds take less time than the initial build, since a lot of stuff will remain cached from the previous builds. Another thing to note are the variables listed there under build configuration. For example, machine, distro version, tune features, and others. These are all quite important, and we have yet to really go into detail about these variables. So I'll be tackling some of those details a little more in the next part of this webinar series. So again, we see there would be over 7,000 tasks to execute here, and that would take a little time. Once the build is complete, we would find that in the deploy directory that there is now an images directory. And inside of there, we find a directory for our Calibri IMX6 machine, and there are several files associated with the image and a number of soft links which simply act as shorter file handles to these very long file names. Here we see the root file system, U-boot, kernel, and device tree files, as well as a tarball which contains the entire image. This tarball is how Toradex distributes its images, and so we'll use it to deploy the image to the target. Okay, so the first thing we'll do is extract this image tarball. We must be sure to do this as super user to preserve the permissions. And now we're going to enter the extracted directory. Without going into great detail, we see that there is a directory with binaries which has the kernel, bootloader and such, and a root file system, as well as a shell script called update.sh. This whole process of deploying the image is rather unapplicable to the Yocto project, but I want to show you how our image booted on the target. All Toradex modules have onboard flash or eMMC, and in the case of the Calibri IMX6, it has an eMMC. So deploying the image means flashing it to the target's onboard eMMC. In other systems, you might instead put the image on the SD card and boot from that. However, our modules are fused to boot from onboard flash. So my point is that this will be a little specific to Toradex modules, perhaps. We'll use the included update.sh script here to write the image to the SD card, which is then used to flash the image to the target's onboard eMMC. So this will take a little time, and I just skip through it there. And now I'm transitioning the SD card to the target. So again, we put the image on the SD card, and now we're going to write it to the target. And I'm switching the console here to the terminal connected to the target's serial console. And now I've booted the target into the bootloader console, which was already on the module. And now we're going to flash the onboard eMMC using the SD card. I'll now enter run set update, which runs some update scripts from the SD card and populates some uboot variables. And now I'm going to run one of those variables called update, which will take care of flashing the image to the onboard eMMC. And this would normally take a little bit of time, probably a minute or two. So again, I'm just going to skip ahead. With the update complete, the system will now boot into the newly flashed image. And here we see the kernel loading. Again, this is the new kernel that we just flashed to the target. And it looks mostly like a happy kernel. There it is, you see angstrom. And finally, we can log into the system. And let's take a look at the kernel version that we just booted here. This is indeed the kernel that we just built. And let's see, let's check engine X as well. We just put that on this image, which is not standard on the Toradex image, but we do see that it's installed, so everything looks good so far. And now the next thing that you likely want to do is develop an application to run on this image. For that, you're going to want to build an SDK. So we'll go back to our host systems console, and we're going to use Bitbake to create an SDK for this image. We just enter Bitbake image name along with -c populate underscore SDK, and again, this will take a little time to generate. So we'll just speed that up a bit. When it completes, we'll have, again, have a look at the deploy directory, and we now find that there is an SDK directory inside as a script, which we'll use to generate an application development environment. And upon executing that script, I'm prompted for a path, which I'll enter. This is the path where our SDK will be installed. And extracting the SDK would take a few seconds. Go to that directory. And once complete, this is what we'll find. We see that there are sysroots for both our target and our host system. These contain libraries, headers, and such that we can build our application against. Also note the environment script. Sourcing the environment script will export a bunch of environment variables used by the application development tools. So let's have a look at that script. We see that it adds some paths to the path variable. It sets a bunch of compiler and linker variables. For example, CC variable here is now pointing to the C cross compiler built as part of the SDK, and also has some of the tune parameters included. Let's now take the SDK for a spin and build a Hello World application. We'll populate the typical Hello World source file here. And now we'll compile it using the SDK's exported C compiler variable. And here we see that it did indeed create a hello binary. And we'll quickly look at the file type information for the hello binary. We see here that yes, it was built for our targets architecture. And now we'll transfer that binary to our target. And I'm going to switch back now to the console on the target, and we're going to run the application on our Calibri IMX6 with our newly flashed image. And there we have it, Hello World. We can cheer now. So that covers what I consider to be the absolute basics. With what we've covered here, you can build an image, deploy it, and begin developing applications for it. But I also want to show you some other useful commands, which I'll just rapidly demonstrate here. To build just the bootloader, use the target virtual/bootloader. And we just built this as part of the image, so it's actually not gonna have to execute any tasks. To build just the kernel, use the target virtual/kernel. And to edit the kernel config using the graphical menu config UI, you can add -c menu config to the build command. Note that this will only edit the config of the kernel in the temporary work directory. Cleaning the recipe or forcing a fetch and reconfigure the kernel recipe will clear any changes made while using this menu config utility. But this can still be useful if you want to quickly build a new kernel with some different kernel configs. And you can also clean recipes. You add the -c clean to the bitbake command. And in fact, you can run many tasks with -c flag. For example, to fetch the source for a recipe, add -c fetch to the build command. Other commonly available tasks are like patch, configure, compile, install, package, among others. And actually, we can actually see all the tasks for a recipe. We just add -c list tasks to the bitbay command. And then these tasks, we'll see all the tasks for a recipe. In this case, we're looking at the kernel. So these are all the tasks that are part of the kernel recipe. So again, we note some of the common ones, also some unique ones like menu config. And to see all the licenses in an image, view the license.manifest file. This is particularly handy in hunting down any licenses which may be incompatible with your project's needs. So here we really see for all the rest, all the packages actually, the license used. And here I'm going to search for GPLv3, as this can be particularly troublesome for some products distribution model. And that actually wraps up my demonstration for this webinar. I just want to make one final remark. The Yocto project and associated tools allow for a lot of versatility in many regards. Workflows are no exception. There is a lot of freedom when it comes to choosing a workflow. That is, there are many degrees of freedom in building and maintaining an image, as well as in developing applications for an image and building and deploying packages. This walkthrough serves as a sort of very simple quasi-textbook example of working with the Yocto project using the Toradex build system. But there are a lot of ways to tailor the system and your workflows to the needs of your projects. And in my opinion, the best way to figure out how all of this can best serve your needs is to begin using it. All the documentation that's out there is certainly useful. Again, the Yocto project documentation is very good. And I hope this webinar is also useful. But I think it's especially useful once you've begun and get a sense of what you ultimately need to achieve for a real project. And for the next part of this webinar, part 2, called the advanced part, I hope to dig into actually customizing an image by creating a new layer, building on top of recipes, and etc. And we'll dig in to some of the more of the metadata and configurations which have a great impact on an image. I want to do that in a walkthrough like I did in this webinar, but in the context of a hypothetical project with realistic requirements. I haven't prepared the material for this yet, so I'd really appreciate your feedback from this webinar and let me know what you'd like to see in part 2. Probably can't address everything, just like I left out a fair amount from this webinar. And although it's labeled advanced, in reality it's only as advanced as one can hope to get in 2 hours of webinar. Okay, so enough of me talking. Let's get to your questions. I want to see what everybody is wondering. I think this question, somebody's had experience with Windows Embedded Compact, and what's the preferred approach on Yocto? We would still like to focus on application development and don't have the manpower to spend much time on BSP-based concerns. What if we switch to Yocto? What would you suggest? So actually, I think that's a good question, because so we do have a lot of customers on Windows Embedded Compact. Toradex takes care of a lot of the BSP on, the whole BSP on Windows Embedded Compact. And so the support there is quite good. However, if you're coming to the Yocto side, things are indeed a little different. Everything is open source except for maybe some proprietary display drivers or graphics drivers from SoC vendors, but by and large, you can get our entire BSP and build it using the Yocto project. So the workflow is quite a bit different, I think, in that regard. As far as support goes, I think you're probably getting good support on either end, but you have probably more freedom with the Yocto project. So if I can, let me know if you have any more specific questions about what your concerns are, and I can try and suggest or try and address those. Okay, what else is here? Add drivers to kernel. Yeah, that's what I'm going to do in part 2. So that's a good point. I think that's one of the more common use cases actually, is that you have to go in and, so our kernel, just for, so everybody knows this, it's really kind of aimed at being an embedded Linux kernel. We don't throw everything into the kernel config, so that's different from what you might see in like a desktop distro. And even modules, we don't configure it to build lots of modules. But so if you want to add support for a device that's not supported out of the box, then you will probably need to say add a config to the kernel, and possibly even include some firmware for example, if you're using a Wi-Fi device. So that's something I do want to demonstrate in the next webinar. Will there be a copy of part 1 of the webinar for download? Yes, it will be on the webinars page. Is the CC part of the SDK? Yes. So CC is set by the SDK generation script. So again, you will need to build the SDK using the populate SDK command with BitBake. It will generate the SDK environment, which you then have to install. And then you will need to source that environment file as part of that SDK. Sourcing that file will set things like that CC variable, which configures the cross compiler and such. You mentioned Toaster. Is it any good? Well, let's see. I don't know if I can be real specific here, but I think it's worth playing with. It's actually rather interesting. As far as how much utility you get out of it, it's maybe, for somebody who only needs to build, like, say, one image, Toaster may not be of great value. If you're the type like us who have basically a dedicated build server and are running builds all the time, then it is quite handy, because then you can see the status of builds and stuff in a more graphical manner. So yeah, I mean, it's worth checking out. Okay, did you try to build Qt4e demo image? So we do have this Qt for embedded demo image, and yes, we've built them. I can't say that we've necessarily, so that probably doesn't, I'm not 100% sure that it supports all of our machines, so that I would have to verify. We actually have documentation about that on our developer website, so if you check out developer.toradex.com and you type in the search, is probably the best way to find it. Type Qt and probably throw in Linux or Yocto, probably Linux, will get you there, and then you would find the documentation about this. So it's a good question, but I will refer to our developer website. I would be interested in how to make a custom or some modifications to a BSP to deal with my hardware. And this is also, again, something I want to do maybe in the next part. So part 2, we'll get into, I want to use a realistic scenario again, adding device support to, say, the kernel and the device tree, possibly some other, also some other configurations. So it depends what modifications you're ultimately talking about here. But yeah, that's something we want to do. You may, we could probably go into some detail here, but I don't want to do too much. But you may end up having to kind of create a new machine configuration. And so a good place to start would be, our machine configurations. For example, the Calibri IMX6 one that we just built. You could copy that and tweak it if you need to make sort of fundamental changes to the machine definition. Okay. Do you build your own compilers for SDK for BitBake? So what we do is we use open source compilers. Now they do get built as part of the build process. So pretty much a lot of that stuff that you saw, even the tools and stuff, a lot of it is built from source. And so that includes the compilers and such. So we have a question. When we build the kernel, it shows that it's dirty. Essentially what this means is that you didn't build the kernel with like a clean git commit. So what you probably did is pulled the kernel source and then made changes to the source. For example, maybe without doing a commit or something like that. And then it shows up as dirty. Let's see. Which Toradex modules can run this image? Well, the one I just built is for the Colibri IMX6 module. And like I was saying earlier, really with the Yocto project, what we're trying to achieve is, commonality across our modules. So really it's the same build system for all our currently supported modules. So whether that be the Vibrid IMX6 modules or Tegras, you should have basically a similar experience. Now, of course, the actual image is different in the end that you build. It's built with a different BSP and such. Yeah, it's same build system. Let's see, is there a QEMU machine available for Toradex VFX modules? Is Toradex working in implementing and providing one? No, not currently. Of course, you can use the QEMU machines, but we don't have one that's tailored specifically for the Vibrid. So, and as far as I know, we haven't worked on one. So if I want to switch hardware platforms, what all changes do I need to make, and in what layers? Well, it kind of depends a little bit on what you mean by switch hardware platforms. I mean, how drastic of a change are we talking? In general, you're probably looking at making a new hardware or a new machine definition. So those are part of the BSP layer. And of course, we have machine definitions, for example, like our Colibri IMX6 or Colibri VF for our Vibrids, Colibri T20, T30, blah, blah, blah. So if you're changing from, say, one module to another, you just change machines. Now, if you're making a rather drastic change, or you're going to a platform which maybe there's not already a BSP or at least a machine definition for that, then you might have some actual work to do. You may have to actually maybe create a BSP layer, or maybe just create a machine kind of configuration. So it depends a little bit. Let's see, next question. Wayland layers work on Toradex boards. So that's not something we really officially support currently. I think we've started testing, so I expect that, I guess what you mean by works is maybe something that varies a bit here. A little bit depends on the graphics support here. So in fact, for many SoCs, the graphics drivers are proprietary and closed source, and so you also kind of need almost like a for example, in X, you have kind of an X11 component, which is kind of special for these proprietary drivers. But, so yeah, I can't really actually give you a straight answer on that question. Is there a QEMU that runs A5? I think there's something that is sort of equivalent. Yeah, I'm not sure, actually. I haven't used it myself, so I would have to look that up. What is the equivalent of a recipe when the embedded system tool chains and images are built using open source tool chains? So I'm trying to think of what this means exactly, but I mean our tool chains are also already open source. So we use Linero tool chains. For example, the Linero cross compilers and that kind of stuff. So If you want to see the recipes for that stuff, you can actually just dig into the meta layer. So there's a meta Linero layer. That's a good place to check for those recipes. Let's see here. And that actually looks like I basically got through the questions that I can tell anyway. So if anybody has any other questions, you know, I'm available. Let's see, what are some common questions that I get from other people? Most people want to, you know, maybe they need to make a tweak to their kernel. You know, maybe they need to add a kernel config for a like a wireless module, you know, Wi-Fi and Bluetooth or something like that. So a lot of people want to know how they should integrate that into their image build. That's the kind of thing that I'll get to actually in part 2 of the webinar. So if you're interested in that, check out part 2. Also building, you know, a special meta layer for your applications or extra packages you require. You know, these specializations like, you know, special kernel configs, device trees. You know, in some of these cases, you'd actually probably officially want to build your own machine configuration. But that's the kind of stuff that we should see in the next part of this webinar. So I think, let's see, I'm not really seeing any other questions here. So I want to thank you all for attending the webinar. It was a pleasure to talk to you today, and I'd really like to get your feedback, what you'd like to see, what you thought, if you think I can improve anything. Toradex is continuing to ramp up our webinar efforts. We want to do even more as far as embedded Linux is concerned. So if you have any thoughts, I'd love to hear them. And again, check out our developer website, developer.com, or developer.toradex.com. Also check out our community website, community.toradex.com. It's a great place to ask questions. If you just want to ask some questions, that's a good place to do it. And I'm going to go ahead and throw my email into the chat here. I think you probably have it somewhere, but you may have received it. But I'm going to go ahead and throw it in here anyway. And you can relay any feedback to me directly is fine.